Hello everyone, I'm happy to introduce my recent work named TIA, a testing framework for detecting consensus failure bugs in blockchain systems with behavior divergent model. As the backbone of the blockchain system, the consensus process coordinates all the nodes in the decentralized network to verify and make agreements on transaction results. The consensus process usually contains many different behaviors. There are four main behaviors. The first behavior is the transaction broadcasting and execution process. The second core behavior is the leader election process. The third behavior is the block steering and synchronization process. And the last behavior is the block validation and confirmation process. Consensus process commonly used in blockchain system can tolerate node crash, failures, and even visiting attacks. The consensus process guarantees four key properties in blockchain systems. They are liveness, safety, integrity, and fairness. Unfortunately, due to the complexity of the node consensus process, it is hard to avoid bugs in the implementation of the consensus process. Any bugs that break these four properties leading to consensus failures are called consensus failure bugs. Here, I show an example of consensus failure bug in physical because in 2022. This vulnerability has been assigned with a CVE ID. This bug occurs in the wheel change process of the leader election behavior. The wheel in cache should be clear to 0 for each from index. Otherwise, a malicious node can constantly send the same wheel change packets to the honest nodes with a large value of wheel to reach. Consequently, all nodes in the system begin the wheel change process uninterruptedly and stop processing other packets such as transaction, blocks, and so on. Attacks can use this bug to easily perform a DOS attack by preventing valid transactions from being processed. To effectively fight consensus failure bugs in blockchain system, there are two main challenges. The first challenge is to come up with precise oracle that can identify whether a blockchain system behaves correctly. Blockchain consensus behaviors are complex and dynamic. Even though vulnerabilities are executed, it is hard to find them without precise detectors. The second challenge is that the CFB tends to be hidden in the deep logic path, making it hard to trick this bug oracle efficiently. The blockchain consensus process usually comes in multiple phases, with many nodes interacting and cooperating in different phases. Multiple nodes are required to execute a series of different behaviors to detect deep path logic vulnerabilities. So we designed TIA. Here is an overview design of TIA. The key insight here is to test blockchain systems consensus process. More abnormal consensus behaviors than those occurring naturally during regular use need to be triggered. As the figure shows, there are two key components. Behavior divergent agent for constantly calculating the behavior difference of the nodes and calculating messages based on it. And Oracle automation for analyzing nodes consensus data and identifying consensus failure bugs in real time. Behavior divergent engine first constructs transactions and messages. Then the messages are sent to the target nodes and the transactions are executed under the blockchain consensus network. Oracle automation collects and analyzes the consensus data of distributed nodes in real time. The difference between this consensus data is calculated, then TIA delivers it to the behavior divergent model for guiding the message further. In the meanwhile, the execution runtime information of nodes will be collected and the difference between them will be calculated. Oracle detector compares the consensus data with the expected data and identifies if the nodes violate the Oracle by checking the consensus difference. Finally, TIA proceeds to the next iteration from step 1 to step 6 of the testing process until termination. First of all, let me introduce the behavior divergent guided further. As we all know, most consensus process of blockchain systems in practice are aimed at guaranteeing the eventual consistency. Transient inconsistencies in node behavior are normal and allowed. However, a key assumption here is that the eventual consensus theory is the cumulative result of many transient inconsistencies in the consensus process. So TIA process behavior divergent guided further to constantly generate plenty of messages and make the nodes in the system behavior as differently as possible. TIA first described the behavior divergent model to calculate the behavior difference between nodes. Two types of data are collected. Consensus data indicates that the core consensus states of each nodes, including leader information, transaction data, block states, and so on. Runtime data presents the key real-time states of each node. All the nodes' behaviors are driven by the messages in the blockchain system. So TIA employs behavior-guided message further to constantly generate messages as input to test the whole blockchain system. Specifically, if a new mutated message detects a new Oracle bug or generates new different behaviors, then they will be stored in the seed pool. In the next fuzzing iteration, they might have higher priority to be executed. In this way, TIA makes these nodes behave as differently as possible and eventually trigger the consensus failure bugs. To help identify consensus failure bug precisely, TIA models for Oracle according to the 4 key properties of blockchain consensus systems: liveness, safety, integrity, and fairness. The first two detectors are transaction related. The liveness Oracle guarantees that all valid transactions must be executed, committed, or stored in a specific block eventually. The safety Oracle guarantees that any invalid transactions are not allowed to be executed, committed, or stored in any blocks. To detect them, TIA first randomly selects some unlocked states from the global states and locks them. For example, the balance of account A is XA. Then TIA constructs two sets of transactions, including valid transaction set and invalid transaction set. In the meanwhile, the expected states are inferred and recorded. Finally, TIA checks whether the transactions are executed by comparing the global states with the expected states. If the valid transactions are not executed within decision time, then a liveness bug is detected. Similarly, if the invalid transactions are executed and stored, then a safety bug is detected. The rest two Oracle are message related. The integrity Oracle guarantees that the block data are consistent in all nodes. Fairness Oracle means that all nodes should have a fair possibility to be elected as the leader nodes or minor nodes. To detect them, TIA first randomly selects some nodes as the target nodes in the network. Then TIA constructs and sends a set of messages to target nodes. Those messages include block-related messages and leader election-related messages. In the meanwhile, TIA constantly monitors their block data and leader data and calculates their data difference in real time. If there is an inconsistency in the data of their local blocks or for a decision time, then an integrity bug is found. Similarly, if the times of being leaders varies greatly for a decision time, then a fairness bug is detected. Here we have to notice that the decision time is really important for the bug detection. In a distributed environment, it is difficult to actually identify whether all nodes are in finality state where all data are fixed. So the decision time mechanism is proposed in tier. It is critical to the precision of the bug detection. Too short decision time leads to many false positives because in distributed scenarios, transaction execution has a certain delay, which depends on the network environment. However, too long decision time affects the efficiency of the testing process since most of the global states remain locked. So we did an empirical study to find a balanced decision time, and it will be discussed later. We have implemented here on 6 blockchain system, including Go Ethereum, EOS, Fabric, Physical because Quorum, and DM. Totally, we have detected 20 bugs in these systems with 5 CVID assigned. To demonstrate whether tier can cover more code of blockchain system compared with state-of-art tools, we compare tier with Peach, Fluffy, and Twins. Fluffy only supports Go Ethereum and Quorum, while Twins only support DMs. From the table, we can find that tier always outperform other tools in all 6 target blockchain systems. To evaluate the influence of the decision time on false positive, we also conducted the experiments that run tier on different decision time values from 1 block confirm time to 15 block confirm time. In the field of blockchain, block confirm time is a commonly used time unit. As shown in table 3, as the decision time increased, the number of false positives reported by tier decreased rapidly from 67 to 0. These statistics demonstrate that a long decision time can effectively reduce false positive. To evaluate the effectiveness of the behavior divergent model, we also conduct the experiments that compares tier with tier minus, the version of tier which disabled the behavior divergent model and generate message randomly. From the table, we can find that with the help of the behavior divergent model, tier can detect all 20 bugs within 24 hours, while tier minus only detects 8 of them. Our future work will mainly focus on the following aspects. First, we would explore more oracles such as a privacy leaking problem or performance issues to further improve tier's bug detector. In addition, we will try to enhance tier with finer feedback guidance for finding more consensus failure bugs. At last, we will try to adapt tier to more blockchain system. Thank you for listening. Please contact me if you have any question.
Thank you. Any questions? Okay, no questions. So let's thank the speaker again.